Okay, so today we're going to take a look at electrons in a periodic potential. So this is an important topic. It sort of is a first introduction to solid state physics. We're basically in the context now of a crystal lattice, and we have a first model that will try to explain what electrons do in such an environment. And so here's sort of a first stab at this. We have an electron, but it basically is in this environment of a lattice with positive ions. Okay, you see them here. And one way we can model that is by thinking about the potential energy landscape again that an electron would see. And so if the electron, for instance, takes a certain path through here, what they would see is whenever they get close to a positive ion, the potential energy drops down quite significantly. So, of course, we're taking here Coulomb's law, right? So minus Q1, Q2 over R squared is the attractive force, but then you can convert that into an energy, a potential energy, and you get minus K Q1, Q2 over R. So technically, if the electron is right on top of the ion, we drop down to minus infinity, okay? And so if the electron is sort of in between ions, it's still negative, but not nearly quite so negative. And we get sort of this kind of bumpy kind of profile for the potential energy that the electron sees. So this is a fairly complicated potential, and so we're going to try to simplify it, and we're going to simplify it by just square pulses. That's what we're going to do. And so here it is again. We have our potential energy as a function of x. We're going to do this in one dimensions, first in one dimension. And this red line here is the potential energy landscape. We're basically going from 0 to V naught, okay? And we have these little barriers here that are of size B, okay? And then we're going to say then this here is a distance A, just to keep everything nice and general. Okay, so that's the setup. On the x-axis, then we start here with this first pulse, although this is not the first pulse. This is just one out of an infinite number of them. But we start here at minus b. Okay, we go to 0, and the next one starts at a, goes to a plus b, and so on. So that's the setup. Okay, we want to see what are the electron energies, but we're going to look for electron energies below V naught. So we're going to look for some kind of energy solution that is like that. So sort of a bound solution. So we're still sort of bound here to this array of pulses. And so we can also think of this as an array of wells, right? So this here is one well, and here's another well. So you can also think of this as, instead of a double well, now we have an infinite number, an infinite array of wells. Okay, so we're looking for energies from 0 to up to V naught. Okay, and that's the problem. And in the wells themselves, where V is equal to 0, well, it's a free electron sinusoidal solutions. In other regions where V is equal to V naught, so that's within the pulses, within the barriers, we can also call it barrier. Here V is equal to V naught, and E is less than V naught, so we have exponential decay or growth solutions. Okay, region 2. This is stuff that we've already done, right? So we get basically in region 1 this kind of differential equation. V is 0, so it doesn't appear here. And then in region 2, we get V naught. Okay, and so we're going to simplify that by using our definitions for alpha squared and gamma squared from before. We've already introduced them. Okay, and so then these two equations become much simpler looking. Okay, just to remind you, okay, alpha squared is 2m over h bar squared times e. And here we flipped it around. It's V naught over minus e times this prefactor. Okay, and we get an additional minus sign out front. So in this way of writing it, then gamma squared clearly is a positive number. Okay, and we have the minus sign out front. Alpha squared, clearly a positive number. Okay, so we know what those solutions will look like. Okay, in region 1, we're going to get sines and cosines, or plane wave solutions of this form. And in a region 2, we're going to get exponential decay and growth solutions. And we have 4 arbitrary constants here, A, B, C, and D. And we have to determine what they are. Okay, so that's the idea. Here's the picture again. Okay. So for instance, in a couple conditions, right? So if we're looking at the origin here, that's always a nice one to choose because x is equal to 0. And when we plug that into the solutions, a whole bunch of stuff disappears. So we want to stitch those 2 solutions together, splice them together at the origin. Sinusoidal here, exponential here. We have to make sure that they meet here at the origin. And so that gives us some nice, gives us a fairly straightforward condition. A plus B is equal to C plus D. Okay. So we also, as we said last time too, we have to not only make them match there, we also have to make the derivatives match at that point. We have to have a smooth overall solution. And so again, we can do the derivatives, plug in 0, set them equal, and we get a second condition here. Okay, this is very similar so far to the problem from before of the step. Okay, so that gives us two algebraic equations, but we have the 4 unknowns, so we need 2 additional ones. And there's a number of ways we could go about it, but one thing is we have to bring in Bloch theorem. Okay, and so let me remind you what the Bloch theorem is. The overall solution, okay, I'm going to call that the splice solution, has to have this form, right? There is a part here that is periodic, just like the potential, and then there is this part here that is not of that periodicity. Here, U has to be periodic, okay, and just to remind you here, the periodicity actually is A plus B. You can kind of see that, right? So here we start at minus B, and here we start at A. So what's that? What is that distance? Well, it's A plus B, right? Or you can say here we start at 0, and here it's A plus B when we start again. We end that pulse at 0, and then here we end that second pulse here at A plus B. So it's clear that the periodicity of this lattice is A plus B. So U has to be periodic over that distance. Okay, so let's take a look at these 2 points here, minus B and A. We could have also used 0 and A plus B, but let's make it simple. And well, it's slightly simpler to use minus B and A. Shouldn't really make a difference. Those 2 points, okay, are separated by a distance A plus B. So whatever the wave function does here, compared to what the wave function does here. Okay. Well, according to Bloch, we've advanced, right, by A plus B. And so we know that whatever the wave function does here, it has to be equal to that, but we allow ourselves a phase factor to come in. They don't have to be identical, but they have to be identical up to this phase factor. That's what Bloch theorem says. Now, it may seem a little odd. It's not a super intuitive thing, but we have to believe it, and that's what it says. Okay, but here comes an additional point now that you have to think about a little bit. Okay, so this is a non-obvious point on top of a non-obvious equation. So just to warn you a little bit here, we're going to say that psi of A, here we're going to actually think of that here to be in region 1. And at minus B, region 2. Okay, so we're stitching those two points together. Okay, before we were sort of at the same point. One is in region 2 and the other one's in region 1. Okay, but so we're at the same point, but now we're stitching 2 points together that are not at the same point. Okay, but we're choosing different regions. So far, so good. So here, by the way, as an aside, I'm following the treatment in Kittel, the famous undergraduate textbook, Introduction to Solid State Physics. Our textbook has a slightly different development, but comes to the same conclusion. So it's nice maybe to read our textbook, those few pages, as sort of a complementary development. I find Kittel's developments are slightly easier, but I could actually go either way. I just wanted to show you maybe another way of getting to the final equations. Okay, and so yeah, so in both treatments, of course, Bloch theorem will be central, so you can't get away from Bloch theorem. Okay, so that's what we're going to do. Here's region 1, and here's region 2. Okay, so now really just math. Okay, so in region, so where I evaluate at A, the wave function at A, I'm going to use the sinusoidal form, and when I evaluate at minus B, I'm going to use the exponential form of the solution. And then I still have this Bloch phase factor in there as well. So I get this equation here, or if I can simplify that just slightly, did I simplify here? Oh, well, just the minus signs here and so on. Okay, so this is basically the same. Okay. And then I can do the same thing for the derivatives again. And I get this equation then. And so now I have my 4 equations. So I've spliced together the wave functions themselves across a distance a plus b. And here I'm going to splice together the derivatives across a distance a plus b. Okay. And so I have my 4 algebraic equations for the 4 unknowns. Okay, and well, here they are again. Okay, a plus b is equal to c plus d from before. I alpha a minus b is equal to gamma d minus c, and then those 2 new ones that we just derived. And the question then is, can we solve that for a, b, c, and d? Those are the only unknowns, really. There's 2 more constants running around. I would not call a constant. I mean, it is a constant, but an unknown constant. A would be given. You know, it could be like, you know, 1 angstrom or 2 angstroms or something, whatever the periodicity of the lattice is. So we would know A, and we would presumably also know B. So those are just 2 distances that define the energy landscape, and I wouldn't call those unknowns. A, B, C, and D are arbitrary constants. They are unknowns, and then you could say, well, the alpha still appears and the gamma still appears. Okay, and so there's still 2 more constants here running around as well. Alpha basically is related to the energy of the solution, alpha squared being 2m over h bar squared times E. So alpha is sort of a placeholder for E in a sense, just vaguely speaking, roughly speaking. Alpha is sort of the energy. And then gamma here has to do with the height of the potential, because there we have the V naught in there as well. So it's 2m over h bar squared quantity V naught minus E, right? So this one also has the height of the barrier in it. So there's a lot going on here, you know, and it's not easy. I mean, it's not easy to approach this by any means. But the idea now is, can we try to solve this for A, B, C, and D in terms of alpha and gamma. And more importantly, even still, is can we even find solutions? We might not even be so interested in what the solutions are, what exactly A, B, C, and D are. We might be more interested in, can we find a solution? Or, I mean, in other words, does a solution exist or not exist? Right? And so you want to think in terms of the broad big picture. Can we even possibly find A, B, C, and D such that we satisfy all four of these equations? Okay, and so the way, from a linear algebra point of view, you would do this is you would convert that into a matrix equation, because it's a linear system, right? And so, for instance, if you look at that first line, matrix multiply, you get +1 times A, well, that's just A, +1 times B, that's just B, plus -1 times C, that's just minus C, plus -1 times D, that's just minus D. And so this first row here would read A plus B minus C minus D is equal to 0, right? So that's what it would read. And if you look at that again here, that's just our first equation: A plus B minus C minus D is equal to 0. Okay, so sorry, folks. Revealing here a little bit too much. Yeah, so here again, so this is the first line. And then you can do this with the second line, third line. I just got a little bit lazy and didn't write out all of them. But again, you would do the same thing. Minus alpha times A, okay, and so on and so forth, is equal to 0. So you can transform those previous four equations into sort of a matrix equation. What do we do now? Well, if you want to get A, B, C, and D, this column vector out, you'd have to invert this matrix, okay, multiply left and right by the inverse. That gives you just, cancels out this here, and you get an inverse matrix times the 0 column vector. Okay, so then anything times 0 is 0, and so then A, B, C, and D would be 0. We don't want that, okay? Hence, this matrix must not be invertible. Otherwise, we only get that solution. If I can invert this matrix, then I can just apply that inverse to both sides, and I'm going to get A, B, C, and D all 0. We don't want that, because that's a trivial solution. We want a non-trivial solution. And so that means this matrix, if there's going to be a solution, then this matrix cannot be invertible. The inverse must not exist. And so that means that the determinant must be 0. Okay, so that's the sort of the thought process here is I need that determinant of this matrix to be 0. Otherwise, I could find the inverse, but I don't want an inverse to exist. And so I need to demand the determinant to be 0. Okay, so the determinant of this 4x4 matrix better be 0. Okay, and so that's what we do. We look at the determinant of this matrix, set it to 0. Then we do some more considerable work that I'm going to spare you, because it's just getting ugly there. But it's really not, in principle, so complex. It's just a lot of nitty-gritty manipulations. So considerable work there, but finally we end up with a constraint coming out of this condition that the determinant be 0. And we finally end up with an equation that needs to be satisfied. Okay, and lo and behold, we do have the gammas and the alphas running around. We still have this k as well running around. That's coming from the Bloch theorem, the k. Okay, so k sort of arbitrary. Okay, so we're hoping that there is some k for which we can satisfy this condition. Now, this equation is still not all that easy. It's still quite complicated, as you can see. Okay, there's hyperbolic cosines and hyperbolic sines running around and so on and so forth. So we do one more simplification and we take the following limit, okay? So basically the motivation for taking this limit now is to make the math easier. Maybe not super satisfying for a physicist, but basically we're gonna say, all right, in order to simplify this, let's think of these barriers as very narrow but very tall. So we're going to let V naught sort of go to infinity while also letting B, the width of these barriers, go to 0. So we're going to do that such that the product remains constant, and we're going to call it the barrier strength. So here's our barrier from before, okay? It had a height of V naught and a width of B. We're going to now make it taller and skinnier, but such that the area here will be preserved. So the area is sort of like how strong are these barriers separating the wells, and how strong are the barriers separating the wells. And when we do this kind of limit, we can sort of say, well, we haven't really changed the barrier strength. In one sense, the problem hasn't really changed that much. The math gets simpler, but the problem hasn't changed. And so that's sort of a physicist's maybe justification for the limit. We're not messing up the problem too much here by doing this, but we're making the math simpler. All right. So then we're gonna introduce basically the following sort of constant capital P, okay, and it's basically proportional to the barrier strength. And there's a prefactor out front too, but that's basically it. And in that case then, when we define it this way, and using this limit, we can show that the previous equation reduces down to something that looks a lot more manageable now. P times the sine of alpha A over alpha A plus the cosine of alpha A is equal to cosine of K times A. So you notice that a bunch of stuff has vanished here. The hyperbolic sines and cosines are gone, and it overall looks simpler. Okay, so just to give you a rough idea of how this happened, okay, yeah, so, or before we do that, just remind you of a couple of things. P here was the barrier strength, alpha, okay, still related to E. And so, for instance, where did the gamma go? Okay, you might ask. We let V naught equal to infinity, and so the gamma squared now is really 2m h bar squared times V naught. We can drop the E here because V naught is basically, when V naught gets large, the E kind of doesn't matter. It completely outshines the E, overwhelms the E. So we can sort of drop in this approximation the E here, okay? And what's also interesting is that this combination gamma times B basically goes to 0, okay? Even though the V naught goes to infinity, the V naught times B stays a constant, then I have an additional B in here, and that B goes to 0, forcing this entire expression to go to 0. And so then the hyperbolic cosine of gamma B, okay, goes to 1, and the hyperbolic sine of gamma times B approaches this gamma times B. Okay, when you then plug this here into the previous equation, see where that is here. So this sinh here would just turn into gamma times B. The cosh here would turn into 1. Okay, and we're also gonna drop the B in here because B goes to 0, right? So then it's really just the cosine K times A. And you know, the gamma squared here is much larger than the alpha squared, and so on. If you do a couple of those things, then you very clearly get, without much work, you can see that this really is what we get. Okay. Okay. So what's the big picture here? It's very easy to get sort of stuck in the particulars, the tiny details with the chronic penny model, because it is very detail oriented. There's a lot of things going on in it. and it's very easy to not see the forest for the trees. But what's the big picture? What's the forest? Well, the really important question we want to ask is, can this equation ever be satisfied? And so if it can be satisfied, what are the values of alpha for which it can be satisfied? All right, so that's sort of the bigger idea. So alpha here is related to E, alpha squared being proportional to E, right? And so when I ask for what values of alpha can we satisfy this equation, what I'm really asking is what energies, what electron energies E, can we have? What energies can the electrons have in this periodic potential? All right, so that's the bigger picture. So let's go back to the equation. So this is our big governing equation now, the chronic penny equation. And the way we want to approach it is by comparing the left side to the right side. And the right side here is just the cosine Ka. And we know about the cosine, it is basically always in the range of -1 to 1. Right, it stays within that band of -1 to 1, and so then that means that the left-hand side better also stay within that band, right? Or alternatively, if this ever gets larger than +1 or less than -1, we cannot find a solution. There's no solution possible. And so one thing when you take a look at that, one thing that you suspect is that as P, the barrier strength, or the thing that is sort of proportional to barrier strength, if that P gets larger and larger, it's going to be harder and harder to satisfy this, clearly, right? It's going to be very hard to keep this less than +1, for instance, when P gets larger and larger. I mean, this cosine here can be as negative as -1. So, yeah, so we can say that for very large P barrier strength, it's hard to solve this equation. But if we go to the opposite limit of P going to 0, so the barrier strength gets weaker and weaker until it entirely vanishes, we kind of know what should happen in that limit, right? Because we don't have these little spikes, these delta functions. We don't have these barriers separating the wells. And so we don't have the barriers separating the wells. The whole thing becomes one giant well. We should basically expect a free electron kind of picture because we have no barriers at all. So what does the equation say here? Well, when P is equal to 0, that whole first term goes away, and we're basically just left with this equation here. And in the simplest case, that just forces the arguments to be the same. In which case, then we can say that alpha has to be equal to K. Okay? And if you square everything, you get alpha squared is equal to K squared. Okay? But we also know that alpha squared is equal to 2m over h bar squared times E. And so now we get this equation here, which I'm going to invert and solve for E. And so we get E is equal to h bar squared K squared over 2m, okay? Which is the exact formula for a free electron. And so there is some self-consistency here going on, that if there is no barriers, if the barrier strength goes to 0, I do recover the energies for a free electron. Okay, in a sort of a roundabout way. So what's left then to explore is what happens when P is not 0. Okay, and the best way to do that is to explore it numerically using Mathematica, for instance, or any other numerical software that you want to use. But Mathematica is particularly useful here in this context. So what we're going to do in class, okay, is to look at Mathematica. So together, interactively, to look at Mathematica, see what Mathematica tells us about the solution for various barrier strengths P. Okay, thank you.